This video is for Math 1342, and we're going to be doing Chapter 3 examples. Okay, Chapter 3, Section 1 is about center of data. And most of this people have seen before in high school and even way down to junior high, although we'll do more with it than that. But the main part of it is from that low, actually. So these are called measures of central tendency. Central tendency, where is the middle of data? What is a typical or average one? There's three main measures that everybody knows from previous math classes. Mean, which is like the mathematical average. This, you add all the numbers up and divide by how many there are. The median is the middle of the data when you put the numbers in order. And the mode is which one occurs most frequently, which one happens the most. Mean, median, mode. There's a couple more we'll look at too, but these are the ones everybody's familiar with. Mean, median, mode. Technically, they can all be called an average. An average is like what's the typical one, but people associate finding average. When you say to somebody, what's your average test score, they're going to take all their test scores, add them up, and divide by how many they have. So that's more commonly associated with the mean, actually. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 11 numbers given to me. That's too big. There. Okay, so I think you can see that better now. There's 11 numbers here, and they're in a mixed-up order. This is what happens when you collect data, is they come to you in any order, and they're always messy to work with, and you can't get any information from them. So it turns out you don't need the numbers in order to find the mean, which we've been doing since junior high. Put it here so you can see every number. My main computer crashed. I'm using a laptop here. So add up all 11 numbers. 95 plus 24 plus 18 plus 69 plus 66 plus 76 plus 26 plus 20 plus 67 plus 19 plus 54 equals, and then divide by 11. You can do this with any calculator at all. We won't really start using the fancy calculator till Chapter 4. Now, sometimes averages are like this where they're really messy. So they'll tell me where to round. It says round, type an integer or a decimal rounded to one decimal place. So if it came out exactly, I would just put the integer, but one decimal place, this is 48.5 because the next digit's a 4. And that next digit has to be 5 or higher on its own. Don't go to this 5 here and say, oh wait, there's a 5 way down here. If I use this 5 to change this 4 to a 5, then it would be a 5, and then I could change this 5 to 6. You don't get to do that more than once. So all you do is look at the second digit. If that's 5 or higher, then you add 1, otherwise you don't. So this is going to stay 48.5. Now, the median, you have to put the numbers in order, and it'll take a while with this problem, but here's what people get sometimes is it'll be like 10, 2, 1, 5, and 7. Say that's your data set, and then somebody asks, what's the median? And people, oh, I know it's supposed to be in the middle, so they try to grab this 1 right here in the middle and say the median's 1. And then they get the answer totally wrong. It's not the one sitting in the middle when the data is first presented to you. You have to collect your data and sort it to do the median. You don't have to sort it to do the mean, but you do for the median. Once you put it in order, 5 is the median because there's an equal number of smaller and bigger values in that number. There's 2 numbers smaller than 5, and there's 2 numbers bigger than 5. That's what makes it a median. So for this data set, let's see, we don't have any single-digit numbers. Teens, there's an 18 and a 19. 18, 19, Any numbers in the 20s? 24, 26, 20. So 20, 24, 26. 20, 24, 26. 30s, no. 40s, no. 50s, just this 54. 60s, we got these three, 66, 67, 69. That's 2, 4, 6, 8, 9. There should be two more. There's a 95 and there's a 76. Okay, so 76 and 95. So one way to do it after you have the numbers in order is just check off the lowest and highest, check off the next lowest and highest, and keep doing that over and over and over again until there's either one or two numbers in the middle. Every time you do a median, there'll always either be one or two in the middle. When there's one in the middle, that's it, just like the shorter example I made up. So 54. If there were two in the middle, then you would average those two, add them up and divide by 2. So the median always works one way or the other. It's pretty easy to do. It just takes a little while if the data is kind of long, and then some people get tricked by not putting it in order. The mode, you don't have to have it in order necessarily to do the mode, but it actually helps if it is in order, because to have a mode, there has to be some repeated numbers, at least one number that repeats. And here, I think every number was different. 18, 19, 20, 24, 26, 54. Yeah, they're all different. If they're all different, then you just instantly say no mode. And just in case we don't see another example of it, so if you have 1, 2, 3, there's no mode. If you have 1, 1, 2, 3, then the mode is 1, because that one's happening twice and the other numbers are happening once. You can even have more than one mode. 1, 1, 2, 2, 3. Now you have 1 and 2. But a misconception is some people think the mode is every number that repeats, and that's not necessarily true. So if you have 1, 1, 1, 2, 2, 3, if that's your data set, then you're back to just 1, because 1 happens more than 2 does. There's 3 1s and there's only 2 2s, so then it's the most. The idea is the most, it's not repeats, but you have to have repeats to have an answer. And you probably wouldn't see this, but by technicality, if every number happens equally, 1, 1, 2, 2, 3, 3, this is supposed to be a 3, then you're back to no mode. So it's not as soon as there's repeats that there's going to be an answer. If every number happens equally, if every number happens once, if every number happens twice, then you're no mode. There's got to be at least one repeat that's different than other repeats. But you can get a whole bunch of answers. If there was 2 1s, 2 2s, 2 3s, 2 4s, 2 5s, and a single 6, then you could have 1, 2, 3, 4, and 5 as your mode. You probably wouldn't see an example like that either. But now, the one calculation that's not taught in junior high or high school, this is the first time you've probably seen this at the college level, is called mid-range. And I don't know if I think the name is kind of a bad name, whoever picked the name for this, mid-range, because we also do other words that have the word range in them, including one that's just the range. We talked about range back in chapter 2, actually, and we're going to talk about it more in section 3.2. Range alone is the maximum number minus the minimum number. It shows you how far spread out the whole data set is. But mid-range is an average of the lowest and highest. So take the maximum or the minimum and add the other one, because order doesn't matter when you're adding. So it's either max plus min or min plus max, and then you divide by 2. It's the same way you find a median when there's 2 numbers in the middle. So if the median has 2 in the middle, you add them up and divide by 2. In the mid-range, you just take the lowest and highest, add them up and divide by 2. So here, the lowest number, here again, you could possibly do this without the numbers being in order, but you might have trouble finding the lowest and highest. So your best bet on if you're doing mean, median mode, and even mid-range is just put the numbers in order right away, because you're going to need it for all the other ones anyway. You have to have it for the median, and it helps on the other ones. for the mean, it doesn't really matter if you do it or not. So if you're only finding a mean, then that's the one time you don't need to put the numbers in order. But if you're going to have a part A, B, C, D, where they want you to do all of them, you may as well just put the numbers in order right away. So 18 is the lowest number, 95 is the highest. I just have to do 18, the mid-range. Mid-range is 18 plus 95 divided by 2. So 18 plus 95, make sure you press equals after that, then divide by 2. And whenever you divide by 2, you either get an integer or you get a number with a 0.5 on it. There's no way to get any other decimal but 56.5. It either comes out exactly or it's 0.5. Some people know how to do a problem and they get it wrong because of maybe their calculator messes them up. 18 plus 95 divided by 2. If you don't press equals in between, it's only going to divide the 95 by 2 and you get a wrong answer and you wouldn't even know it probably. So you've got to know how to operate your calculator so you don't mess it up. So now I forgot what I had. It was 56.5. The correct answer was 56.5. Not that 60 number that was incorrect. Okay, what do the results tell us? So these are jersey numbers of 11 players of some team, like a soccer team or a football team. Well, the problem is jersey numbers, even though there's numbers and you can do math with them, you can physically do math with them, but these are actually meaningless calculations. You wouldn't say what's the average player number on a roster of players because the numbers are like names. We just put numbers for names sometimes because it's easier to identify people. It's easier for computers to work with it. But jersey numbers are actually nominal data, kind of like when we talked about phone numbers. They just identify somebody. So really, these are all meaningless calculations to do the mean, median, maybe the mode's okay, but the other ones are meaningless calculations. So the jersey numbers are nominal and they do not measure or count anything, so the resulting statistics are meaningless. Unless they mention mode. Mode could be interesting, but you can do mode for nominal data if you have like colors, like which colors pick the most. That could be meaningful. But in sports, no team has multiple people with the same number on it. So I'm just making sure the other answers don't say anything about that, but it should be A, about how it's kind of meaningless. You can physically do it, but it's kind of meaningless. It's like my example I gave about Alaska, where if the high temperature is 0 one day and if it's going to be twice as cold the next day, you can do 0 times 2, but it turns out to be meaningless because how can it be twice as cold if the temperature didn't change? Okay, so that was the first problem, and then it looks like this is just another example of it. I think the reason this one's also in the homework is there's 2, 4, 6, 8, 10, just to show you what happens if there's an even amount of numbers. Because a second ago we had 11 numbers, now we have 10. Okay, so it looks like the numbers are not in order exactly, but it looks like they're in order backwards actually, so that could help me to do everything without sorting them myself. But for the mean, you don't need them in order. I'll just type them in the order they are. 275 plus 190 plus 175 plus 170. And then we got 2 different 165s. And then the last 4 numbers are all 155. And there's 10 numbers here, so when you divide by 10, it's really just going to move the decimal over. We're going to get exactly 176 for the average here, for the mean. 176. So for finding the mean, it doesn't matter if you have an even amount of numbers or an odd amount of numbers. You do it the same every time. You just add them up on how many are there. But for the median, it matters. When there was 11 numbers, I had exactly 1 in the middle. But now that there's 10 numbers, there's going to be 2 in the middle. So if you eliminate the lowest and highest and keep doing that, the 2 in the middle are these 2 165s right here. There's 4 numbers bigger and there's 4 numbers smaller, since these are already kind of in order backwards. So the answer is 165, but if you didn't know that, the average of 2 numbers that are both the same is itself. So the average of 165 and 165 is 165, and you can add it up and divide by 2 if you don't know that. But if you get a 90 on your first test and a 90 on your second test, your test average will be 90. There's not really a reason to calculate it. So the median is 165 here. So technically I had to add 2 numbers up and divide by 2 when there's an even amount of them. And see, this is a good example compared to number 1 to do the mode, because in number 1, every number was different. Now we have repeats. There are 2 165s and there's 4 155s, so then it's only the one with the most. It's not both of those repeats. It's only 155. Again, that's a common misconception. People think it's every single number that repeats. And then the mid-range, I take the highest plus the lowest and divide by 2. It's pretty easy to do it, but unfortunately you're going to probably get it mixed up with other calculations that have the word range in them. 275 plus 155, press equals, and then divide by 2, 215. And these are millions of dollars of celebrities, how much each celebrity is worth. So money is something that we count. Money is discrete, so these are meaningful calculations. If we have I guess these are the highest celebrity amounts, so what they're worth. So then the top 10 celebrity money that they made maybe in a year, or just what they're worth for their whole career. You can do averages of that and the median and the mode. These ones are meaningful calculations, since the data is it's not just categorical or nominal. The results tell us the most common celebrity net worth is the mode, but all our celebrities are expected to have net worths approximately equal to the mean. No, it's definitely not B. So it's very rare if the mean, the median, and the mid-range, or even if you include the mode or not, it's very rare if all the answers are the same. Notice these answers are all different. 155, 165, 176, 215, they're all different. Usually they're different. They can be all the same, but if the mean, median, mode are all the same, then you have very symmetrical data. And usually data that you collect is not symmetrical. Apart from the fact that all other celebrities have amounts of net worth lower, they do not give meaningful results. The results from Part C, most common. So one thing that could be true here, even though the calculations are meaningful, I think what's going on here is in this question where it says, what do the results tell us about the population of all celebrities? See, that's the problem here. If you want to know something about all celebrities, you don't want to pick the 10 richest celebrities. That's the problem, is this sample doesn't mirror the population at all. If you want to know what does an average American do for a salary, you don't want to look at the 10 richest people in America or even the 10 poorest. So they should have gotten a random sample of celebrities, not just pick the 10 richest celebrities. So apart from the fact that all other celebrities have amounts of net worth lower, the results do not give meaningful results. The most common celebrity net worth is equal to the mode. That is true. Apart from the fact that all other celebrities have amounts of net worth lower than those given, nothing meaningful can be known about the population. So it might be this A, just because that's the idea, is that they're only looking at the 10 richest celebrities. So you can't really know anything about the rest of the population. You just know that they all have lesser net worth, but you can't figure anything out about what's typical among them. So this one should be A because of that fact. So even if the data is, remember number 1, the issue with 1 was it was really nominal or categorical data. You can't really do math with that. You can physically do math, but it's not meaningful math. In number 2, this was meaningful math, but the problem was the sample was bad. You don't want to take the 10 highest of any population. That's never going to tell you what's happening to the typical one. So I guess there's another question about any problems with this. Based on the nature of the amounts, what can be inferred about their precision? See, this is another thing. I think we saw this in an earlier chapter too when we were doing one of those charts. See how every number ends with a 5 or a 0? That's usually when people estimate what their net worth is instead of actually calculating it. So the values all end in 0 or 5, so they appear to be rounded estimates. They're either rounded or estimated when people do that. So that can throw the results off too. If you ask somebody, how much money did you make last year? And they don't know, so they say, I made 50,000. And they're just guessing the number off the top of their head and rounding it to something convenient. If you get enough rounded and estimated answers, that can throw the results off. So the author here was trying to show that was very good what he did on the first 2 problems, where number 1 was the issue with 1 was, even though you can physically calculate things, it was kind of meaningless since the data was just people's names in essence. Numbers were names. And then 2 could have been good, but the problem was that the way they took the sample really messed it up. Okay, you can also do the mean, median, and mode in what's called grouped data, where you get a frequency distribution. Now, these also will not be exact because we have one person or one time when the temperature was between 40 and 44, but we don't know which. Was it 40? Was it 41? Was it 42? We don't know. 9 times the temperature was between 50 and 54. We don't know which one. Maybe all 9 of them were 50, or maybe there were some different ones. So what you do for the mean is, the best you can do for this is you assume that every one that occurs in a given interval happens exactly in the middle. That kind of balances it out. So if there were some low ones and some high ones, they're probably going to be on average in the middle. So the middle of 40 to 44, halfway between those 2 numbers, is 42. And if you can't do that in your head, 40 plus 44 divided by 2. So basically what we're going to do is make a chart here, and I'm going to put midpoints in one column. This is problem number 3. I'm going to do the midpoints in one column. The midpoint of the first interval is 42, and then you're going to still keep the frequency here. There was one of those. There are 7 numbers between 45 and 49, so if you do 45 plus 49 divided by 2, that's 47, because they're 4 away from each other, so if you go 2 away from the lower, 2 away from the higher, you'll hit the same number. So 47 has 7 of those. So out of the 7 numbers between 45 and 49, there could be different ones. There could be some 45, some 46s, some 47s, some 48s, and 49s. There's going to have to be some repeats, though, because there's only 5 numbers in that range, and we have 7 times that happened. But we have no way to know in this group data how many of each individual number happened. So the only fair thing to do is assume they're all right in the middle, because it's probably going to average close to the middle anyway. So we're going to assume all 9 of these are right in the middle of 52. 52, all 9 of them. If we actually had the raw data, it probably wouldn't be exactly this, but it turns out this gets pretty close when this is the best you can do. So assume all 4 of these are 57s. Notice this is going up by 5s every time too. Then once you get a couple done, then you might be able to figure out the rest without actually calculating. So then halfway between 60 and 64 is 62, and there's 3 of those. So make a product column. Just multiply straight across. If all 7 of the second one are 47, well then 7 times 47 is what it would actually add up to if I knew every single one of them. So 1 times 42 is 42. 47 times 7 is 329. 52 times 9 is 468. 57 times 4, 228. And 62 times 3, 186. Add this up. 186 plus 228 plus 468 plus 329, and plus 42. This calculation right here, this 1253, this is literally similar to if I knew every individual number and I added them all up. That's what this would be close to. It probably won't equal it exactly, but it would be pretty close. So when you find an average, you normally add up all the numbers and divide by how many there are. How many are there? That's what frequency is all about. Frequency is how many times each thing occurred. So add up the frequencies. 1 plus 9 is 10. 7 plus 3 is 10. That's 20, 24. There were 24 values here. So if I divide this by 24, this will get me a good estimate of what the real average would have been, and I have no other way to do it anyway. So 52.2, maybe they want nearest 10th. One decimal place, 52.2. Yeah, nearest 10th. 52.2. Notice also that if you look at the temperatures, there's 1, 2, 3, 4, 5 different ranges, and 52 is near the middle of the middle one. So that this is a very reasonable answer. Gives you an idea what the middle's close to. Okay, which of the following best describes the relationship between the computed mean and the actual mean? So I think they tell us what the real mean actually was, like somebody actually had the raw data and actually added all 24 of them up and divided by 24. The actual mean was 52.5, according to the directions. There'd be no way for us to know that, but 52.5, and we got 52.2. That's pretty close. That's not that far off. So the computed mean is close to the actual mean because the difference is less than 5. If you're less than 5%, then that's pretty close. And I'm not going to calculate it, but it's close enough that I can assume that's less than 5%. And that's the idea that you hope happens, is the calculated mean will be close to the real mean if it's not too far away, so you don't want it to be more than 5% away. Okay, another thing you can do is called a weighted mean, and in fact, any college class you're in basically grades your grade in the class as a weighted mean, and your GPA is actually a weighted mean too. So a student got a B, C, A, B, and D in 5 classes one semester, but some of them are 4 credit classes, one was a 3 credit class, and one was even a 2 credit class. In fact, in our class, 1342 is a 3 credit class, but the 0242 grade is a 2 credit class. The grading system assigns quality points to the letter grades, and we probably all know this, that an A is worth 4, a B is worth 3, C is worth 2, D is worth 1, F is worth 0. Find their grade point average. Okay, so this person got, here's the grades they got. They got a B, CA, B, and D in their 5 classes. B's are worth 3 points, A's are worth 4, C's are worth 2, and D is worth 1. But then there's also how many credits each class is worth. The higher credit class is going to weigh more into your GPA. It's better to get an A in a 4 credit class than to get an A in a 2 credit class for your GPA. If you're going to have a D, it's better to have a D in a 2 credit class than in a 3 or 4 credit class. So the credits were 4, 4, 4, 3, 2, apparently in that order. 4, 4, 4, 3, and 2. So luckily, the one they did the worst on was the 2 credit class. That's going to help their GPA than if that was somewhere else. Very similar to number 3, you just make a product column. Multiply this out. 4 times 3 is 12. 2 times 4 is 8. 4 times 4 is 16. 3 times 3 is 9. It's supposed to be a 16. And 1 times 2 is 2. You always add the product column in both of these scenarios. You add the product column, and that's what you're going to do first in the calculator. And then you add one of the other 2 columns, and that's what you're going to divide by. So 12 plus 8 is 20, plus 16 is 36, plus 9 is 45, plus 2 is 47. And yes, you could just use a calculator, add it up. What we want to divide by is how many credits we took. So add up the credits. 4, 8, 12, 15, 16, 17. So their GPA for this semester is 47 divided by 17. See, if every class was 3 credits, if you had 5 3-credit classes, then you could just average your grades and you wouldn't care about the credit. But since some credits are higher than others, that's called a weighted average. The ones that are higher weigh more into the average. So 47 divided by 17, and keep in mind a GPA is like 4.0, 3, 2, something like that. And this student has pretty average grades up and down the scale. They should be somewhere in the middle. So a 2.76 seems very reasonable for a GPA for somebody who doesn't have straight A's. 2.76, maybe they're going to make it 2.8. I got to see what they want it rounded to, but probably 2.8. No, it does want 2 decimals, so 2.76. You always got to read that blue part. Type an integer or a decimal rounded to 2 decimals. So 2.76 is this person's GPA. This student did not make the dean's list because their GPA is lower than or less than 3. Apparently you got to be 3 or higher to make the dean's list. So they were a little bit lower than that. Okay, so here's another example. This is the one I was talking about, is both your GPA and every class you take is a weighted average, really. So here's somebody's in one class, and this class has a midterm that counts 10% of the grade. So make a chart here. So midterm is worth 10%. One class project is 5%. So we got a project, 5%. They got homework is 50% of their grade. In our class, it's 20%. And the final exam is 35. In our class, the final is 20 also. But here it's 35. Now, one thing that's always true about school classes or college classes is the percentages have to add up to 100 in a school setting. This column doesn't have to add up to 100 in other places. Notice here it only added up to 17. So, but if you get a school problem about a grade in a college class, then one nice thing is you're always going to add that up and it should be 100%. So then we need to know what were their grades in each of these categories. Just like you're going to have a test average and a homework average and a final exam grade, and your grade is calculated very similarly here. So this guy got a 73 on his midterm. That's a C. He got a 97 on his project. That's an A. A 75 was his homework average. That's back to a C level. And his final exam was a 63. That was the worst one. Usually finals are most people's worst grade because it's the hardest test and it covers everything. So he worked really hard on the project. That was good, but the problem is that's the one that's worth the least. You want to get your highest grade on the one that counts the most, which is the homework. And that's just an effort area. So I do a similar thing when students come close to a grade. I look and see how much effort did they put into these effort areas. Okay, as usual, you always make a product column. Just go straight across and multiply. It turns out you can do this in decimals or in percentages. It works either way, so I'm just going to keep it in percentages. 10 times 73 is literally 730. You just put a 0 on the end of it. 97 times 5 is 485. 50 times 75 is 3750. 35 times 63, 2205. You always add the product column, and that's always the thing you have in the top of your division. So 2205 plus 3750 plus 485 plus 730. That is 7170. So you're going to do this divided by the sum of one of the other two columns. That's how all of these work, is you get the product divided by one of the other two columns. So you at least got a 50-50 chance every time. The product column divided by one of the other columns added up. So how do you know which one to add up? Well, in school setting, this is the easiest one to remember because you always divide by the 100%. You want to divide by the column you don't want the answer to be. I'm looking for the person's average grade. I want to know what is their average grade so I can give them an A, B, C, or D. I don't care what the average percent is. The average percent doesn't mean anything to me. So whatever you want the answer to be, average grade, I want the answer to be grade, then you don't divide by the grade. Divide by the other column. So that way the 7170, that's the product column. Dividing by 100 is the percent column, and then the answer is grade. That way each column is being used once. One of the three columns is always the answer. And dividing by 100 is nice because you just move the decimal over twice. So this is 71.7. This person would get a 71.7 for a grade. That would be a C, because usually C's are in the 70s. And luckily they got this high project grade because their final was low, and that one counted a lot too. And they could have fallen out of the C range down into the D range if they didn't have one of these categories being pretty high. So 71.7, type in integer or a decimal, and there's no rounding because it's exactly 71.7. When you divide by 100, it came out exactly. And that's a C grade, obviously. Most schools would call that a C. So anything in the 70s is a C. 90s are usually A's and 80s are B's. It even says that in the directions here. So you can do that in this class and all your classes. When you go into D2L and look at your grades, it shows you your overall average at any point in each of your individual grades, but it's really just doing what problem number 5 did. The program is doing that calculation for you. Okay, so notice that question 5 has a 3.1 on it and then 34 for the number. That's section 3.1, problem 34. Now in question 6, we're in section 3.2. And the first problem is section 3.2. So 3.1 is about the center of data, central tendency. And there's the three main ones that everybody knows from junior high. Plus there's a fourth one they do in college called mid-range. A very similar thing happens in section 3.2. This is how does data spread out, or what they call variation. How does it vary? Variation, spread, dispersion is another word. There's three main calculations here: range, variance, and standard deviation. Very similar to how you get mean, median, and mode. Range and standard deviation are both very easy. Range is simply max minus min. It's easy to do, but it's also easy to mix it up with other calculations that have the word range in it. Standard deviation is very easy. You just do the square root of the variance. So once you get the variance answer, if you square root it, you'll instantly have the standard deviation answer. The variance isn't like mathematically hard to do. It's just kind of long because it's a 5-step process. And in essence, standard deviation is the 6th step of the process. Okay, so the heights, 134 heights of males from a data set of body measurements vary as low as 152 and to a high of 194.9. Use the range rule of thumb to estimate the standard deviation. So the range rule of thumb says take the range. This will give you a rough idea of standard deviation because finding standard deviation, actually calculating it, takes a long time. So if somebody wants a rough estimate, it's often not extremely close, but it can give you a fair idea. Take the highest number, 194.5, subtract the lowest number, 152. This is called range when you do max minus min. And if you divide the range by 4, somebody just decided 4 was a good thing to divide it by. Range divided by 4 gives you a rough estimate of standard deviation. It says type an integer around to 2 decimals, so I'll make this 10.73. 10.73. And the actual standard deviation, somebody actually took the time to calculate it. Apparently it's 8.21 right here in the paragraph. So we're off a little bit. We got 10 point something, 10.7, and it's actually 8.2. What does the result suggest about the accuracy? Assume estimate is accurate if it's within 1.3 centimeters. See, this is not within 1.3. It's off by more than 2. 10.7 minus 8.3. It's more than 2 centimeters away, and you have to be within 1.3 to say it's pretty accurate. This is not all that accurate then. This approximation is not accurate because the range rule of thumb is more than or greater than 1.3 centimeters away. 10.7 is more than 1.3 away from 8.2 is what they're saying here. So it's a really rough idea. They used to do it more in the past before we had calculators that could do these easily. So it's still they bring it up sometimes. Okay, another issue that comes up is, this is going to be certainly more important when we get to future chapters. It really matters if you're talking about a population or a sample. That makes a big deal sometimes in how things are calculated. And then people get these symbols mixed up. So the symbol for sample standard deviation, it turns out sample information is usually English letters, and population values are usually Greek letters when you're doing statistics. So sample standard deviation starts with an S, so they decided, yeah, let's just use S for that. And variance, since variance and standard deviation are square and square roots of each other, if you know the standard deviation, you can square it to get variance. Or if you know the variance, you can square root to get standard deviation. So they are square and square root of each other. So sample variance is simply S squared. Then we use Greek letters for population values. So if you do population standard deviation, that's the Greek letter sigma. And if you do it for variance, you just square it, so it's sigma squared. So just so you know, you're going to see these symbols a lot. And I get people confused. They show up to my office hours sometimes, and they say, I don't understand what this R in the problem is. And I'm like, R, where do you see an R? And they point at it. And what they're pointing at is this Greek letter sigma, which looks like this. You kind of go across with a horizontal line, and then you just curl back around again. This is the Greek letter sigma. And it's used for population standard deviation. If you're doing sample standard deviation, then we just use S, but population standard deviation is sigma. So I understand why they're confused. It's a Greek letter from a foreign language, and you know how like sororities and fraternities use Greek letters too. I guess that's why they decided to do it. But yeah, they probably never seen the Greek alphabet before is the problem, but it's not, I don't know why they think it's letter R. It doesn't look like an R to me at all. But I get that a lot where people say, oh, I don't understand what this R is. But so that's why this is a good homework problem, so you understand which symbol is which. Okay, units. Okay, these are standard deviation and variance are actually the standard deviation should be regular units, and then since the variance is regular units for standard deviation, and then since the variance is squared, then it would be square units. Okay. Weights measured in grams, okay. Yeah, and that kind of makes sense, just like in geometry, how like the diameter or the side of a figure is regular units, but if you do area, it's squared, so then you get square units. We don't put units into answers too often, so that's not a big issue on that second half of that problem. Okay, so now I think in number 8, I think we're going to do we're going to do range, variance, and standard deviation all in the same problem. So range is easy if you just get the highest minus the lowest. Now the data is mixed up, but there isn't too many data values here. It looks like the highest one is 271 minus the lowest one is 106. Max minus min is always range. It's pretty easy to do, 165. And this would just be regular units, so dollars, since these prices are listed in dollars. When you subtract, it doesn't square the units, so. Okay, they only want standard deviation. Sometimes they make you find, okay, they do want all three. That's weird. Find the range, variance, and standard deviation, the directions say. But for some reason, the answer wants standard deviation next. You really can't do standard deviation directly without doing the variance first. So I would just go ahead and do the variance next, and then you can get the standard deviation from it. Okay, so number 8, variance is a 5-step process. Luckily, all the steps are easy to do, especially with a calculator, but you got to just memorize the steps. So basically, there's 5 steps here. Step 1, you find the mean, like we did since junior high. That's easy. Add them up and divide by how many there are. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 numbers here. Let me move this so you can see them all. 149 plus 128 plus 271 plus 268 plus 170. Whoops, didn't get the plus. Plus 170 plus 106 plus 159 plus and 138. So this adds up to 1389, and as I counted already, there's 8 numbers here, so divide by 8. And unfortunately, it's a messy number, but 173.625. Okay, next thing we do is, this was the person who invented this calculation was about 100 years ago, and this was their thought, was let's take each given number that I have in my data set, we'll just call each one x, take each given number and subtract the mean. How far is each number from the mean? That shows you how spread out they are. Okay, so the first number is, and here's what I'm going to do. I'm going to store this in memory. This is called memory store. I'm going to store this mean in memory since it's not easy to remember. Take 149. That's the first number. 149 minus memory recall. And then press equals. So the first number is 24.625 below the mean. That's why it's negative. Negative 24.625. So the second number is 128 minus memory recall for the average. And then this one's 45 below the mean, negative 45.625. You just got to do this for all 8 of them. The third number is 271, so 271 minus the mean is above the mean, 173.625. Then we got a 268. Wait, I think I didn't press enter on that one. Okay, let me do that one again. 271 minus memory recall. Okay, yeah, I forgot to hit equals is what happened. So that was 97.375. What caught me was I knew they couldn't all end with that 625 decimal. So 97.375. Okay, the fourth one is 268. See, in this calculator, you have to hit 268 minus memory recall. That's the average. This one's 73. So then I got to press equals 94.375. So one nice thing here is if it's above average, it's going to have a 375 decimal. When it's below average, it'll have that 625. Okay, so how many have I done now? 4 of them. The fifth number is 170. Minus, this one's below average, so I should get that 625 on it. Negative 3.625. Then we have 106. 106 minus the memory recall average is negative 67.625. Two more. There's a 159. 159 minus the average is negative 14.625. And finally, 138. Most of the numbers are below average, actually. So 6 of the 8 are negative subtractions, negative 35.625. But here's something that's true as well. If you take, I'll add this up from the bottom up, take negative 35.625 plus 14.625 negative plus 67.625 negative plus 3.625 negative plus 94.375 plus 97.375 plus 45.625 negative plus 24.625 negative. What's going to happen here, unless I have some calculation error, this is a good double check, because when I press equals, this better say 0. See, it's 0. The sum of this column is always 0 no matter what, because that's basically what the definition of a mean is. A mean is a balancing point, so it balances out the positive and negative distances. Even if there's more positives or more negatives, there's not always an equal number of them. Sometimes when there's 8 numbers, you get 4 that are positive and 4 that are negative. And sometimes there's like a positive 10 and a negative 10 and a positive 3 and a negative 3. And you really can see that they're canceling each other out. But sometimes this happens where they're all weird numbers and there's some big positives and some small negatives. And because there's more negatives than positives, all the negatives end up canceling all the positives. So it didn't make sense to this person 100 years ago. If this adds up to 0, how can I say that the spread is 0? Variance measures spread. How can the spread be 0 if these numbers are clearly not the only way it should be 0 is if all the numbers were the same. If all 8 of my numbers were 7, 7, 7, 7, 7, 7, 7, then the spread of them should be 0, but clearly these are spread out. But it's just due to the fact that the mean is a balancing point in the middle of the numbers somewhere where the positive and negative distances get balanced. So the person had to choose one of two things. There's one of two ways in math to make negatives go away. One of them is absolute value, and the other one is squaring things. Anytime you square something, it's positive. And they chose squaring, although then that creates another issue, but one good thing is any number squared is positive, so I can even type it in positively. I don't need the negative version. You can put the negative if you want, but when you square it, it's going to be positive. So how far do they want me to round this? 1 decimal place. Okay, there is a danger in that if you get these long, messy decimals and round it off a little, that could throw the result off. Let me try it with maybe 3 decimals. 606. They should have given me better numbers to work with here, but 391. So you can actually type it in without the negative, and once you square it, it's not going to matter. So I'm going to type it not negative and then square it. 2081.641. 2081.641. 2081.641. Okay, so the next one's 97.375. Square that. 9481. It really should have been there, but I had to cross it out. 891. Okay, then we got a 94.375 squared. 8906.641. See how they're all ending with a 1 too. Okay, then we got 3.625 squared, 13.141, 67.625 squared is 4573. 0.141. Two more to go. 14.625 squared, 213.891, and 35.625 squared. 1269.141. Okay, so add all this up. I've got, now I can't even read my writing on the first one. What was the first one? 24.625 squared, 606. Okay, I couldn't read if that was a zero. 606.391 plus 2081.641 plus 9481.891 plus 8906.641 plus 13.141 plus 4573.141 plus 213.891 and finally 1269.141. See, this will not add up to 0 because they're all positive. So this is step 4, is to add up all the squares. The sum of all the squares is step 4. And normally if you had better numbers to work with, there wouldn't be this kind of craziness of all these messy decimals. 27,145.878. Okay, the fifth step is going to be the answer to variance, although it depends if you do population or sample. So that's why we had those symbols. I got to check if they want a population or a sample. This says sample data.